Okay, Paul here, and today we're going to do an experiment. We've got a fan here that has a swollen capacitor. According to the leading person, uh, technician basically on fan restoration on the um, um, Antique Fan Association website, uh, the proper replacement for 1.7, and he listed as 1.7. It's actually 1.75. The proper replacement capacitor, because of the increased voltage today, is 1.5. Well, we're going to do a test and see if that's the case. So what I did is and we'll look at this closer after we do the experiment. You'll get to see it up close. But right now I want you to see the whole setting. Okay, what I got it wired just the way it originally was with the swollen capacitor here that is dangerous. And I've got my voltmeter here on AC volts across the capacitor. Now the voltage on the capacitor, and I've seen a lot of people ask this question on the Antique Farm website. They just seem to take it for granted because they don't understand the mathematics. So they just say that it's going to be higher, and it always is higher. But the reason it is higher is because of the motor. The stator of the motor has two coils. It has a starting coil and a running coil. Actually, there's two coils. That's why there's three wires going to the stator. They actually connect together. So I left a little room here where I can show you how that looks. You have a coil that comes up like this, and then you have a bigger coil that comes down here, and then they go out. And there's a wire here, and that's the third wire. And so this is an auxiliary coil. It's not really an starting coil, it's an auxiliary coil. It does help with starting in these Emerson fans. And this is the run coil, or the main coil. Well, if you know anything about transformers, when you have a voltage coming into a coil, and you have another coil over here, the voltage here, AC voltage going through this coil, induces a voltage here. And if you have a lot of windings here on the primary side, and you can think auxiliary coil, and you have few windings on the secondary side, the voltage is going, this is called a step-up transformer. The voltage here is going to be higher than the voltage here. That's why when you measure the voltage across this capacitor, you're seeing a higher voltage. Because even though these two coils are connected together like one long coil, you're feeding your voltage in across this coil, it's going to induce a different voltage across here. So the voltage across here on the capacitor is going to be higher. And so that's just because even though it's a coil, right, it's actually it's sort of like a variac. It's a auto transformer, because you got to tap off a regular like a transformer, like a straight coil, but you got to tap off of it. Well, those coils are going to interact with one another based on the voltages across them. That's why we have different resistances. You remember we had a high resistance here, and then we had a high resistance here, but we had actually I take that back. We had a high resistance here, the highest resistance was here, and a low resistance here when we measured the resistance on all three wires. This one has a low resistance because it's a bigger coil with less turns than this small coil that has a lot of turns. So there's a high resistance here. Two of these are connected together. So there's even a higher resistance here because it goes through this high resistance and then adds that little resistance, right? But when you tap off here, you have a low resistance across this one. So this one's going to have a higher voltage because it's got a lower resistance. And that's how transformers work. But when we're talking about motor, it's a little bit different, right? They're in a circle. They're not separated by an iron core next to each other. They're actually wrapped in a circle on an iron core. So you got a little bit of variation there. Okay, well anyway, that aside, we're going to look at the actual mathematics here and do an experiment. So we're comparing theory with reality, okay? We got to deal with this, so we want to be as accurate as we can. Now, I've read on some of the documentation that was written on old antique fan motors, written a long time ago, that you go up, okay? And that you do the same or go up, which is what you do with radios, right? You use the same value or a higher value. You don't go down in value because you want to filter out hum in a radio. But here it's not the same thing. We're not trying to filter anything out. We're dealing with providing torque to the motor so that the motor has the ability to stop faster and run better. And that's the purpose of the capacitor, okay? But they say that because of today's voltage changes, and I'm going to put a light on this a little bit, because of today's voltage changes, you want to go down because the reason for that, or the logic for that, is what we call X of C. You know, when we talk about electronics, we talk about resistance, right? If you have a signal, a voltage coming in, there's a voltage drop across a load or a resistor. We call that resistor a load. And the voltage drop across that load is where power is being used, right? Because we're losing we're losing the voltage. It's dropping across the load, so the power is dropping. And that's how we determine power. And well, also that's how we determine current, right? Current equals the voltage divided by the resistance. Okay, well, when we talk about capacitors or coils, we're talking about a different kind of resistance. If you measure this across here, when we did, I forget what the reading was, it was like, I don't know, 170 ohms or some ridiculous amount. It was really low, right, because it's DC resistance. If you put 170 ohms across your voltage, your outlet, you're going to trip the breaker because the current's going to go through the roof. But because this is a coil, it has what's called X of L, or inductive reactance. And basically, that's a resistance that's not DC resistance. It's not like a resistor. It's the amount of pressure it takes to create the magnetic field. And then the amount of energy that's released when the magnetic field is collapsed around the coil. So, and that's what makes the motor turn, is those magnetic fields. So there's a voltage drop across the motor that's from making the magnetic field. And it's a lot more than what you measure with a DC ohm meter, okay, or a digital meter. Same thing with a capacitor. The resistance on a capacitor is infinite. Resistance on a coil is really low, DC resistance. On a capacitor, a good capacitor, it's infinite. There's no electricity going through. It's impossible for DC to get through a good capacitor because these two terminals do not touch each other, okay? So that resistance is really high, and we call that X of C. So where this is really low, this one, X of C, where inductive reactance in the motor is really low, capacitive reactance is really high. And that's why they put the capacitor in there. It helps cancel out the inductive reactance because they're opposites. So the two opposites balance out one another, and that's what the capacitor is for. It's to balance out some of that inductive reactance of the coils, okay? So that's what the capacitor does. That's its job, is to balance out that inductive reactance of the motor coil. Okay, now, there's another issue, and that is the reason they are opposites is because how you calculate x of c and x of l. X of l, and I'll write it here, x of l equals 2 times pi, which is 3.1415962 and on, right? 2 times pi times the frequency, which in all of our measurements, the frequency is 60 hertz because we're in America and AC lines, mains lines are at 60 hertz. So we know these, 2 pi fc, f, we know all these. But x of l is 2 pi fl. And L is the inductance of the coil. It's a measurement, just like capacitors have a measurement in microfarads. Inductors have a measurement in henries or microhenries, depending on the size of the coil. Okay, so they're measured in capacitance. These are measured in henries, while the L is the henries. So x of L is 2 pi time, or 3, or you can think of it as 6.28. 6.28 times 60 hertz times the inductance in henries gives us the x of L, and that is given in ohms. Just like a resistor, you know, when we measured the DC resistance of the coil, we got a DC resistance in pure ohms. X of L is also measured in ohms, but it's called X of L because it's not DC ohms. It's inductive reactance making that magnetic field. Capacitance is measured in X of C. X of C is also in ohms. The capacitance reactance is also in ohms, but it's a different reactance. My error there on which is which, it doesn't matter. But the reason they're opposites is you can see here, x of L is 2 pi FL. X of C is, look at, 2 pi FC. But it's 1 over 2 pi FC. It's the inverse of 2 pi FC, or the reciprocal of 2 pi FC. Where x of L is 2 pi FL, x of C is the reciprocal or inverse of 2 pi FC. It's 1 divided by 2 pi FC. So it's totally like 180 degrees out of phase, right? They're totally different. They're opposites. This one is straight, multiply it all out. This one is divide 1 by it multiplied out, which is going to give you a really small number. This will give you a different number. Okay, so I have a suicide connection here, and I understand that. I also have my watt meter up here, which you can't see, which right now is saying that my mains voltage, it fluctuates, right? When I first set up, it was 121.6. Right now, it's 123.4. That's the voltage unloaded or without a load. There's nothing there. It's just the voltage on the outlet. You can't see it, but trust me, it's there. It says 123. I just went to 123.5. So I'm going to change this so that our numbers are a little easier to understand to 123.5, because right now that's what it is. And that changes based on what happens on the power grid, right? A lot of people got their heat on, the voltage is going to drop because there's a bigger load on the power lines. If everybody's temperature is warming up and they're shutting the heat off, because we're in November here, and they're shutting the heat off, the the amount of load goes down, the voltage goes up. And so you see it's already climbing because it's getting a little warmer outside and heat is shutting down. Or motors running and then they shut the motors off. Or cook stoves running and you shut the cook stoves off. Or people ironing and then they shut their iron off. All these things affect the mains voltage across the power grid. But we're only concerned with what's coming into this circuit. And right now, 123.5 is coming into this circuit, okay, as soon as I plug it in. Now, this is a suicide setup here. I got a straight line cord with jumper cables and probe meter wires, everything connected, okay? And I'm going to be switching the power on and off here by hand. There's a lot of risk here of getting a shock or even electrocuted. So do not do this at home. If you do this at home, you're doing it at your own, under your own risk, because this is deadly voltage and you don't want to be playing with it. But I'm about to plug it in, okay? So now it's plugged in. I still have 123.5 volts going to this circuit, but the switch is off, okay? So now what we're going to measure is the voltage across this capacitor. So right now on this capacitor, which is the motor's running on high on its original capacitor, which is rated at 1.75 volts, we've got 225 volts across this capacitor right now. That's why it's dangerous, right? It's boiling in there. That's why it's swelling up. 225 volts. But we only have 123 volts coming in. So 100 volts more on this capacitor. All right? Now the current going through the whole circuit is, according to my meter, 0.15 amps. So I'm going to put 0.15 amps. The wattage being used right now is 13.8 watts. So I'm going to put 13.8 watts. PF stands for power factor. The power factor right now is 0.7. So 0.7 is the power factor according to what we're measuring. And the volt amps, we're not going to worry about that now, or the X of C. We'll calculate that after we get these done. So now I'm going to shut it off. And I'm going to replace this capacitor with a different capacitor. And the way I'm going to do that, I'm going to leave this one here, this lead being used because it goes to this coil. But I'm going to disconnect these on this side. Now the one is the line voltage coming in. That's this one, okay? The other one is my meter. So we don't want this to touch anything because that's the line voltage coming in. And this is just my meter that's measuring the voltage. So the next thing we're going to do is look at a 1 microfarad capacitor. And we're going to compare these. So I'm going to connect a 1 microfarad capacitor here. And I'm going to connect it to the power. So it's got 120 volts coming into it. And I'm going to get another connector. I'll use a yellow wire. And that's going to go, so yeah, because we're measuring the voltage right across this capacitor. So I'm just going to hook this on here. Okay. I'm going to set that aside so I can get to my paper, make sure I don't touch the metal can or anything. Okay. And now I'm going to turn that on and we're going to check this. We did the 1.75. Now we're going to look at what if we went down to 1 microfarad instead of 1.75, which is what they say to do, is go down. They don't say to go down that low. Okay, so now you see instead of 225 volts across that capacitor, we only got 190 volts across this capacitor. So the voltage across the capacitor is better. It's less. Okay, the amperage is 0.19, so it went up. okay? The wattage is 11.2, so it's gone down, which means there's a problem because the current went up, but the wattage came down. Well, if the wattage came down, it's because the voltage come down, because wattage, parent wattage is voltage times amps. But let's look at the power factor. It's 0.47. So the power factor is really bad, because power factor is a scale of 0 to 1, 1 being the best. It's 0.47. It was 0.7, so we dropped the voltage, but the current went up, the wattage went down. It's using less power, but the power factor is worse. It's not as good as it was. So I'm going to shut this off. And probably what I should do is just unplug this. That would be the safest way. Okay, I'm going to, so now that's off because I unplugged it. I'm going to go to 1.5. Well, I don't have a 1.5 capacitor, but I have a 0.5 capacitor here. And if I put two capacitors in parallel rather, they add up. So I'm just going to connect this one across there, and we'll take a look at it, and you'll see it's 1.5 or thereabouts. Okay, put that there, and stick this here. And there's no voltage now, I got it shut off. Okay, so I can go right to capacitance scale because I'm going to cross the capacitor. And you'll see what the capacitance is. Let's take this off here and put it right on the capacitor. Disconnect this totally out of the circuit so that we're not getting false readings from that coil there. Let me just twist that a little bit, make a better connection. Okay, there you go. So I'm calling that 1.5, it's 1.4, it's close enough, right? It's 1.41. So 1.5, give or take 10%, right? All right, so we know that that's right. And I'm going to just leave this here because it's the same thing as having it over there, but I got to connect the power to there. So we're going to put that there. All I'm using this for is a way to get to this coil. So now I'm going to go back to voltage. We just verified that we are roughly 1.5, and I'm going to plug this back in. The fan's going to spin again. The fan's spinning on high. Okay, at approximately 1.5, we have 213 volts, or 214 actually, 214 volts across these two capacitors, which is a 1.5 equivalent of a 1.5 capacitor. That's more in keeping with the original, right? The original was 2.25 or 225. We're now at 214. That's not bad. That's really close. Okay, the amperage is 0.16. Again, really close. 0.15 was that one. 0.16 is these two. It's pretty much there, right? Wattage. The wattage is 11.7. Now we're getting even better because the wattage is still low. We're still not using a lot of power, but the numbers are jiving, which means that this is going to be nice. Let's see what it is. Power factor. 0.58. Well, it's not great, but it's better than 0.47. Okay, so 0.58 is the power factor. So figure 0.6. It was 0.7. It's pretty close, right? All of these numbers are really close. But the voltage going to the motor is less than it was with that. So the voltage going to the motor means less wear and tear on the coil, and that's why they suggest going down. All right, the next thing we want to do is try 2. And to get 2, all right, I'm going to shut the power off here. I think they came unplugged. Instead of putting this, and these, by the way, hold the charge, but I'm watching the voltage here. They discharged pretty fast. So be careful. Just because you unplug something doesn't mean that it doesn't have any voltage. Okay, you should always discharge them. Instead of putting a point, and see this was a 0.47, so that's why it was 1.4 1.41 instead of 1.5. But still close enough. Instead of putting a 0.5 and a 1 to make 1.5, I'm going to put 2 0.1s, which will make 2. Okay, and of course these will be even easier because I can twist these. These are stranded wire. I can twist them together. All right, now we'll connect that back up. That goes there. This goes back on here. This goes back on here to get a reading. And we're going to plug it back in. So, well, before I plug it back in, let me show you that we have, oh, and this goes on here. Before I connect that, let me show you that we do have about 2 microfarads. .95, so 2 microfarads. Okay, so now we're going to connect the power back up. So put it back on voltage, connect the power back up, plug it in. Okay, the fan's going to spin again on high. It's spinning. Oh, no, it ain't. Okay. What do I get wrong? Oh, it fell off. That's what I got wrong. All right, plug it up again. Okay, now the fan's spinning. And we've got 235 volts across here. So that went up. And the current draw is 0.16. So the current didn't go up. The voltage across the capacitors went up. 0.16, so they're the same. The wattage is now almost 17 watts. It's 16.9. So the wattage went way up. And the power factor probably came down since it's using more wattage. Went up, which would mean a better power factor, and it did. It's 0.81. So that's actually the best power factor. That's better than this capacitor's power factor. And we'll talk more about that in a minute. Okay, so the voltage goes up, the current stays the same. The wattage goes up because it's roughly these times each other, right? And the power factor went up. But we're putting a lot of strain on the motor because we're running a higher voltage to these coils. But they're more in sync, basically. All right, so let's shut this off. I'm going to take these off, and we're going to do the last one, which is 2.5. So now we're going to 2.5. Okay. And so now I'm going to plug it back in. And the voltage is 240, so it went up even more. It's actually 241. Current is 0.22, so it went up. And I'm doing this a little bit faster because I ain't too crazy about it. 24.4. And the power factor is 0.89. Best power factor of all. Okay, let me shut it off. All right, and shut this off. Now we have our chart. We can go over it. I'm going to connect this back to the original just so I don't have to try to figure out how everything went. This really doesn't matter. This is that don't matter either. What matters is these. It's that green wire. That's all that I need to know. Okay. So what does this all mean? Well, let me zoom in here. when you're talking with motors and transformers, and you're talking about power, most of the time you'll see something like a motor will, well, motors are usually in horsepower and you have to convert it to a wattage. But for like transformers, um, you'll see something like um, 150 volt amps, or it'll be rated 1.5 k volt amps. I know it's 1500 volt amps. You know, that's how they'll rate them. What that is that's called the apparent power. Apparent power is, you know, in DC, power in DC equals voltage times the current. So if you got, um, let's say 10 volts DC times 5 amps, you have, that equals 50 watts. And that's exact power in DC. Now this is DC, power DC. So we'll put a little DC there. Power DC. In other words, you got a 10 volt battery, like in your car. Let's make it 12, better yet. So you got a 12 volt battery in your car. You're drawing 5 amps to your radio or your brake lights or whatever. You're using 60 watts of power out of the battery. Okay, that's the exact formula. Power equals voltage times current. But in alternating circuits, in AC, you have, if it's just a resistor, if I had a resistor and nothing else, it would still be voltage times the current. But if I have a capacitor, the current and the voltage are not in phase. Look at the wattage. You have to use a whole lot of wattage in this system. In other words, a lot of capacitance to match this motor. And it takes a lot of wattage, which means it takes a lot of voltage and a lot of current at that point when you're at a high power factor. You're using a lot of voltage, a lot of current. You notice that these multiplied together, 0.2 times 24, that's like almost 1/10, right? 24, okay? So it's actually, it ain't even there yet, right? Because 2 times 24, 0.2 times 24 would be 48, so it'd be 48, okay? But it'll never get to 48. It's 0.89 power factor. It'd have to be 1 to be 48. So you see how the power factor really is a determination. Well, what that is you're dealing with two kinds of power. When we talk volt amps, we call that apparent power. That's apparent power. That would be we would consider power. Voltage times current. Voltage times amps. Current is in amps, voltage is in volts. So 150 volt amps means 150 volts times amps. We would normally say that's 150 watts, but it's not. It's apparent power. Now, if it was DC, it would be 150 watts, and that would be called actual power. So the way power factor works is they take the actual wattage that's being used, which the watt meter measures, and you divide it by the volt amps. And when you divide it by the volt amps, you get a power factor. You get a factor. It's just basically a factor between actual wattage and apparent wattage. Actual power and apparent power, okay? And that's what we got. This is apparent power, voltage times amps, or VA. So we're going to do that. So if we take a calculator, 225 times try again. 225 times 0.15 equals 33.75 watts. So the apparent power is 33.7 watts, or 33.8 actually. We'll say 0.8 and round it up. 33.8. The actual watts is 13.8. That's what we're using. But the apparent wattage is 33.8 watts, which is a whole lot higher, right? And if you divide, all right, so let me put that in, okay, well, let me just clear it. If you divide 13.8, the actual watts, divided by the apparent watts, you get 0.408. So even that isn't actually correct. The meter up there is saying it's 0.7, but it's really 0.408 or 0.41. So that's strange. Let's put that over here, 0.41. And this is calculated PF. This is measured PF. So there might be some problem between some inductive reactance going on between the transformer out on the telephone pole and the transformer or the coils in the fan, which is making this discrepancy. Because remember, transformers have inductive reactance. So the transformers on the power grid out on the telephone pole outside my house has inductive reactance that's reacting with the inductive reactance of the fan. So the meter is measuring 0.7. Now the meter is measuring correctly because it's an electronic device that's actually responding to, actual voltage and current, to calculate these out. But anyway, let's do a couple more and see if this gets even closer to the truth. Let's do the next one. The volts is 190 times 0.19 equals 36. So 36, it's 36.1. We clear this. We have 11.2 watts being consumed divided by 36 equals 0.31. So now that's closer, 0.31. And the meter's saying 0.47. So this is actually closer to being true. Let's try the next one. We've got 214 times 0.16 equals 34.24, so we'll say 34. And if we clear that, the measured by the meter is 11.7. Whoop, get that calculator back. 11.7. 11.7 made me gun shy. Divided by 34 equals 0.34. And you see how they're going, they're like not really going in any particular way, right? Okay, and I think I see something else that I'll talk about in just a second. Because I'm doing this too, just like you, right? We're doing this together. Now, voltage here is 235, clear, 235 times current is 0.16. Current's staying pretty constant. Try that again. 235 times 0.16. It's not doing the point. Clear. 235 times point. Thank you. 16 equals 37.6. All right, so that'd be 38. Clear. And we have 16.2 17.9 or 17 divided by 38.44. And according to the meter, it's 0.81. I see what's happening. Okay, let's try the last one. 241 times 0.22 equals, no, Claire didn't do it. 241 times 0.22 equals 53. And Claire, 24.4 divided by 53 equals 0.46. Okay, so we're 0.41, 31, 34, 44, 46. These are going up, but remember this one is really 0.175 is really right here. So that makes sense, right? 31, 34, 41, 44, 46. You see how they're going up? Here, this one, again, remember we looked at the original one first. It's really in between these two. So 11.2, well, let's look at that measured power factor. 4.7, 58, 0.58, 0.7, 0.81, 0.89, they're going up, right? The amperage, 19, 16, 15, 16, so they're about the same. 22, okay. Current was a little bit less in here because this joker has got some internal resistance, and that's why it's swelling up. This capacitor is swelling up. That should be 16 at least. It's 15, so it's, you know, it's 10 milliamps less because it's being burnt up as heat. Now look at the voltage. 190, 214, 225, because that's next. 235, 241. It's going up, right? Okay. What about this one? Again, this is here. Well, we've seen that. What about the volt amps? 36, 34, 33.8. Then it goes up. 38, 53. Okay. Look at the power factor. 0.47, 0.58 or 0.6, 0.58, 0.7, 0.81, 0.89. You see how they go? They're going up together. Everything is moving together. So if we look at just, if we forget the original one, because we know it fits right in where it belongs, and look at just these, you see, this is the only exception, and that might be a math error on my part, because we got 31, 34, 44, 46. 47, 58, 81, 89. They're going up. 11, 2, 11, 7, 16, 9, 24, 4. 19. Now we do have a drop in current here to 16, which makes that really nice because it's dropping the current and raising the voltage. That's pretty good. So this seems to be a valley here in the current. And then it starts to turn around. 2.0, it stays the same, and then it goes back up. So you see how in this range here, the current actually drops and then sort of floats around in here before it starts to go back up. So it's like a V, right? It's high here, it's low, and then it's high here. You see how that's going? Okay. And if we plug this in here where it goes, it's actually in the peak between the two. So 1.75 is the best current. That's why they engineered it for 1.75 for this fan. However, the voltage is much lower at 1.5, say 214, and that's because of our mains of 123.5. Now, when this fan was made, it was made for 110 and 15 volts. So we got, 8 volts higher than what the fan is rated. That's driving the voltages up here. This voltage is high for what this capacitor was designed for. In fact, it has a maximum voltage here. It's hard for me to read that. A maximum voltage of 220 volts. And look, running on mains, it's getting 225 volts. Do you see why it's swelling up and wanting to pop? At 123 volts going in, this joker has more voltage than its maximum allowable voltage. And that's why it's swelling up and about to bust. Okay, this capacitor. That's why it's swelling up and about to bust. It's only rated for a maximum of 220 volts, but it's getting 225 volts. But if you look at this, where the capacitor is dropped by just 0.25 from its original, just 0.25 of a microfarad, look at the difference in the voltage. 225, which is above what this can stand, versus 214. But look at the current. They're almost identical, right? The voltage dropped, the current just barely climbed, all right? Look at the wattage. It's using less power to do the same amount of work, okay? It was using 13.8 watts with this capacitor at this voltage to spin that fan. But with a 1.5 capacitor, it's using less voltage, drawing the same current, but the power is less. It's only taking 11.7 watts to do the same amount of work. So you're saving on your electric bill, right? The power factor is not as good, but when we look at this, we see that the calculated power factor is really close, between 0.34 and 0.41. Why are these different than these? Because we are not measuring, this is measuring the power factor of the whole circuit in relationship to the transformers and everything else. But what we're calculating here is the power factor across the capacitor. So this capacitor, these are the capacitive values of the power factor of the capacitor. It doesn't matter. You see what's happening here. Even though these are different, this is calculated, this is actual measured. I'm not sure why that's 0.7, probably, like I said, internal resistance there. The rest of these are not that far off, okay? So you figure those are twice as much. So there's probably some inefficiency going on, internal resistance. You know, when we get to the 2 and the 2.5, you see how the power factor goes way up, which means what's actually being measured is better than what we're calculating. Why? I don't know. I don't know. Because this is the formula. You can search online for power factor, and that's the formula you'll get. It's wattage divided by the volt amps. Real power divided by apparent power. And the real power, according to the meter, now, you know, I'm going by the meter, the real power, and you can look at the numbers and kind of get an idea that they're close. The real power is 16.9 watts. The apparent power is 38 watts. So that's a big discrepancy, right? 17 versus 38, it's over twice as much. Same thing here, it's over twice as much. And it may be that the capacitor with the coil working together is actually making more problem for the motor, I don't know. But this is perfect in comparison to that. It's perfect. And if you look at the calculated, they're close. The apparent, 0.7, 0.6, I mean, that's factor of what, 10? 1/10? That, you know, that's nothing. It's within 10%. So I'm thinking this is the best. The reason being, one, we're dropping the voltage. Well, we got to change it. They don't make 1.75 capacitors. That's just not even feasible. Everything is now is made within a 20% tolerance because everything is plus or minus 20%. So if you got 10, the next thing you make is 12 because 10 plus 20% is 12. The next thing they would make is, 12 plus 20%, which would be 10 would be 1.2, so it would be 2.4. So it would be 14.4 would be the next one. You see? So that's how they climb, is by their tolerance. So a 1.5 is the closest we can get to a 1.75 without doing something like this, which would be crazy. But we don't need to, because you see here, 1 does this, 2 does this, 1.75 does this. They're all within the exact same range. They're all close together. And this is a little bit too high voltage. This is the best, 1, but that may be too much work for the motor because the power factor is kind of low there, 0.47, 0.31. Here we're closer to the original. So that's why they recommend 1.5. So that's what I'm going to put in here is a 1.5. And unfortunately, I don't have any 1.5s. I've been using them all up on fans. That's why I had to do this, to create one to do the test. But I've got them on order, and they're being shipped out today. I'll have them Wednesday. So I bought a bunch of them. So going forward, I have them for these these Emerson fans, because I got another Emerson out there that's got the same capacitor in it. Okay, what else can we look at here? Oh, the X of C, the resistance. Basically, the X of C is 1 over 2 pi FC. So the way we would calculate, this is impedance, right, resistance. So let's do the 1.75 first. If we multiply 2, and here's the formula, 2 times pi, which is 3.14, okay, we'll just stop there, times the frequency, which is 60 hertz, times 1.75 microfarads, so we got to convert it to farads, which means it's 6, this is 6.000050175. So go back, times 0.12345 equals, that number is, and I'm only going to do these two, 0.003065594. Okay, that's this one here, the one that come with it. Now I'm going to take the reciprocal of that, so clear that. 1 divided by 0.00003065594 equals. This one has an impedance of 1.5 kilo ohms. Okay, 1,516. So 1.5 kilo ohms. Now if we do this one, and we multiply that out again, so 2 times pi, 3.14 times 60 hertz times 0.1234515 equals, that number is 0.0005652. You see they're close, right? Now if we take the reciprocal of that, 1 divided by 1.0005652 equals 17.69, or 1769 at 1.77 k ohms. So this has a, well, actually, don't go there. We're looking at the one that I'm going to put in there. It's 1.77 k ohms. So that's 0.2 k ohms more, or 200 ohms more, 270 ohms more. 270 ohms more means the current is going to stay about the same, right? And it did, 15 and 16. The wattage drops. The wattage drops because we're dropping the voltage across this resistance. However, the voltage also drops, so the power factor dropped, but the power factor is still within reason of what it was, what it should be. So all the way around, this is better for the fan because this resistance is higher, which means less energy is being consumed by the fan to do the same amount of work. So the fan's not working as hard at 123 volts. Now, there's something else to consider. This capacitor is rated at 220 volts, and it's running at 225, which is why it's burning up, swelling, and about to bust. This capacitor, or when I get this capacitor at 1.5, it's going to be a 450 volt capacitor, and it's only going to see 214. It's not going to be nowhere near halfway up to its maximum voltage, where this one is seeing more voltage than its maximum allowed voltage. Right? That's not good. It's like when you're cooking a turkey and you want it at 350 degrees, but you set the oven at 450, you're going to have one dry turkey for Thanksgiving. And that's what's happening here. This turkey is bad. We don't want to eat that one when it blows up. So, and it's swollen, top and bottom.